Welcome to Eager Space. This is episode 4 on our series, where we'll look at how satellites and debris are tracked and how that data is used to predict their future paths. This is the U.S. Space Surveillance Network, or at least the public, ground-based parts of the network. Red dots are sites dedicated to the network, yellow dots are multi-use, and green dots contribute data to the network. The network was originally created to track ballistic missiles. These circled yellow dots all use large, phased array radars. They are very big radar installations, such as the Cobra Dane installation on Shemya Island, Alaska. You may have seen rotating antenna radar on ships. They are very good at providing 360-degree coverage, but their size is limited because they rotate around, and that limits the amount of power they can use, and therefore their detection range. Phased arrays use a one- or two-dimensional array of transmission and reception cells. Looking at the one-dimensional case, if we pulse all the elements at once, each of the elements will send out a bit of energy, and those pulses will combine to give us a high-energy pulse headed in one direction. The pulse is high energy, but a pulse that only points in one direction isn't very useful. But if we pulse them sequentially, the individual pulses combine based upon when they occurred, and we get a pulse that is at an angle to the radar. Phased array radars typically allow the radar beam to be steered 60 degrees to each side, or about 120 degrees of coverage. It's also possible to divide the elements into sections and use them independently. Phased arrays are common in military applications. The U.S. Navy's Ticonderoga-class cruisers have phased array radars on all 4 sides. This F-15 Eagle has a phased array radar on the front. The problem is that phased arrays have been expensive. Instead of one radar transmitter and receiver, every element has the electronics to both send and receive radar signals. An aircraft radar like this one might cost $5 million. Electronics, however, continue to get cheaper. You've likely heard that the Starlink home station uses a phased array antenna, and they can also be found in automobile driver assist applications. And Qualcomm has developed a 5G cell phone antenna that uses phased array technology. That's enough about the tech. Back to the U.S. surveillance system. This is PAVE-PAWS, a 2-sided phased array radar located at Beale Air Force Base in California. Like Cobra Dane, the radar array is nearly horizontal, which means it's not looking up, it's looking sideways towards the horizon. These large radars are aimed at the horizon to detect ballistic missiles as they come over the horizon. That is their primary reason for existing. It just turns out that if you have a very large, and therefore very sensitive, phased array radar that is in continuous operation, you can also use it to track objects in orbit. This large phased array radar at Eglin Air Force Base in Florida is dedicated purely to orbital tracking, and it's roughly aimed at the geostationary belt above the equator. Throughout this series, I've said that 10 centimeters is the minimum size object that is tracked. And the spacetrack.org website confirms that number. But looking back, the first reference I could find to that number is a 1987 paper referencing a 1984 paper that is unavailable. That makes me wonder whether that's the current performance. 1984 was a long time ago. But if we look back, we see that the AN FPS 85 in Florida dates to 1969, Cobra Dane dates to 1977, and PAVE-PAWS dates from 1980. I guess it wouldn't be very surprising if performance isn't any better, since new radars haven't been built since 1984. Which brings me to this chart, which shows the performance of the U.S. Space Surveillance Network across different object sizes. That shows the 10-centimeter lower limit the current system has when it comes to tracking. The system can detect 10-centimeter objects to the top of low Earth orbit at 2,000 kilometers, and its performance drops off at higher altitudes, and it can only detect 1-meter objects at geostationary altitudes. That is not unexpected with a radar. The strength of the radar pulse and the reflection from the object decrease as the distance is greater. I would also expect the performance to be better at 400 kilometers than at 2,000 kilometers, but the chart I took this from doesn't show it. There is a helpful annotation that says boundaries are notional, where notional means theoretical or speculative, so it's not showing the actual performance. Below this 10 centimeter notional boundary, there are 3 additional radars that give us information on smaller objects. The MIT Lincoln Space Surveillance Complex in Westford, Massachusetts, yes, the location that gave us the Westford needles, hosts the Haystack HAX and Huzu radars, both using conventional dish radar antennas. The large radio antennas at NASA's Goldstone Deep Space Communications Complex in California are also used. These radars are used to gather population data on orbital debris, but they do not track individual objects. NASA has done some analysis on smaller object populations based on objects that have spent a lot of time in space. One study uses an instrument from the Hubble Space Telescope. The Wide Field Planetary Camera 2 was installed during a servicing mission in 1993, and when it was replaced in 2009, the old camera was returned for analysis. NASA identified 685 impact craters on the camera's exposed radiator. In 1984, NASA launched the Long Duration Exposure Facility, a satellite designed to expose a wide variety of materials to the low Earth orbit environment for about a year. Because of a series of delays, including the loss of Challenger, it wasn't retrieved until 1990, nearly 6 years later. NASA looked at the rectangular framework that held the material panels and identified more than 10,000 orbital debris impacts. The analysis using Hubble and LDEF therefore give us some information on orbital debris at the smallest sizes. All the data on orbital debris feeds into NASA's Orbital Debris Modeling Program, known as ORDM. ORDM can take information on the orbit of your spacecraft, the altitude, inclination, and eccentricity, and tell you what the expected debris flux will be for that satellite. This chart is more of an overview. It shows the debris flux at different altitudes. The big lesson: 800 kilometers is not a happy place to be. And that's a story on government orbital debris tracking, at least the data available to the public. The Air Force Maui Optical and Supercomputing Site is at the top of Haleakala on the Hawaiian island of Maui, and at 10,000 feet it is above quite a bit of the atmosphere. It hosts the ES-MCAT telescope, designed to track objects at geosynchronous orbit and beyond. The NASA Orbital Debris Office has used data from this telescope. It's widely believed that one of the primary uses of this telescope is to image spacecraft. This is an image of the shuttle Columbia from one of the telescopes at this site. There are other Air Force optical telescopes at other sites around the world. But it turns out that we aren't quite done with radar installations yet. Kwajalein Atoll is northeast of Australia in the Pacific Ocean. This is an excellent site because it is only 8 degrees north of the equator and can therefore see all orbital traffic. The site is known as the Space Fence and hosts the AN-FSY-3 phased array radar. It uses horizontal arrays because it wants to look up rather than at the horizon, and they are very large, with 36,000 transmit elements and 86,000 receive elements. It not surprisingly has better performance than the legacy systems. It is reportedly able to track objects roughly the size of a marble, or about 1 centimeter in low Earth orbit. The NASA estimate from 2015 is that there are approximately 500,000 objects of this size or larger, a much larger population than at 10 centimeters and above. If you want to get access to this information, you can make a simple request, and the government will tell you no. There are some reports that they use this full data set for orbital conjunction prediction, but it is not publicly available. You might have noticed that I specifically talked about government programs. There are a number of commercial companies that are doing orbital debris tracking. These companies have their own sensor networks that they are using to gather data. Some companies use optical tracking with single telescopes or telescopes in arrays. Some use ground-based phased array radar, sometimes in one-dimensional configurations, sometimes in two-dimensional arrays. And there's starting to be satellite-based sensors. How good are these systems? It's not very clear. Everybody claims less than 10 centimeters because that's what the public space track data says. Some claim 1 to 2 centimeters, or that they plan to get to 1 to 2 centimeters with future equipment. Different technology has different strengths. Visual light optical can do very well, but it varies based on lighting, while radar is more consistent. For this data to be useful, update speed matters a lot. It's not useful to track all 1 centimeter debris if it takes you 2 weeks to update your catalog, because the future path can't be predicted accurately for very long. This is a very new industry, and I expect to see the usual mergers and exits. As an example, and so that I can show their very nice visualization page, Leo Labs says that they are currently tracking 26,566 objects. They claim less than 10 centimeters, but with their current radars, they probably aren't much better than that. SpaceTrack is tracking about 66,000 objects. That puts Leo Labs in the same ballpark as SpaceTrack, so I'd say they're pretty close to 10 centimeters. Their stats say that 90% of their objects are updated at least once a day. Decent, but not quite the 3 times a day that SpaceTrack can do. How good can the commercial companies get? Everybody is hoping to get to 1 centimeter because there's so much collision potential in that class of object, and they are largely untracked at this point. I'm thinking there's potential for the radar sites to track a lot of objects in the 1 to 10 centimeter range, and if that data is combined with the optical data, good coverage is possible. It is, however, a really hard problem. And then there's Starlink. SpaceX has more satellites in orbit than anybody else by at least an order of magnitude, and protecting those satellites is of major importance to them. They therefore built their own object tracking system named Stargaze. Pretty much every satellite uses what are called star trackers. They are optical sensors that look at the stars and use the patterns of stars to identify where the star tracker is pointing. Use 3 star trackers and you end up with a pretty good idea of the attitude of your spacecraft, where it is pointing, and how it is rotated. Starlink has 10,000 satellites, and therefore they have 30,000 star trackers. The Starlink star trackers capture video, so not only can they capture fixed stars, they can also capture moving objects. Objects like other satellites or orbital debris. Put a multitude of observations together, do a lot of fancy math, and you can track a lot of objects. And I think this might perhaps be a solution to a puzzle I ran into earlier in the series. The International Space Station is about 109 meters long, and it is very wide. A Starlink version 2 has a total length of about 30 meters. Starlinks are much smaller in area than the ISS. NASA uses a 1 in 10,000 probability threshold to decide whether they should move crewed spacecraft to avoid debris. SpaceX uses the same 1 in 10,000 probability for Starlink. SpaceX reported that they made 300,000 orbital adjustments in the Starlink fleet in 2025. Spread that over 10,000 satellites, and that means about 30 adjustments per satellite per year. The ISS dodges approximately 3 times per year, and there's only one ISS. The Very Large ISS dodges only about 10% of the number of times that Starlink satellites dodge. That's the puzzle. I can think of a few possible explanations, but one is that Stargaze is finding objects in the 1 centimeter to 10 centimeter range, and SpaceX is using that information to avoid them. We don't have a lot of information on Stargaze yet, but we do know that SpaceX has said that they will be making the Stargaze conjunction data, the results of the analysis of all the objects, available to all operators free of charge. It's not clear how that will affect the object tracking companies I just talked about. Now that we have the data, we would like to use it to predict the future path of objects and look for possible collisions. One problem we have is that the area around the Earth isn't a perfect vacuum, and therefore we have to figure out what the aerodynamic drag is. We can use this simple equation. It depends upon the atmospheric density. There is a model known as NRLM-SISE00, which predicts the atmospheric density at different altitudes based upon solar activity. The activity level of the sun causes the atmosphere to expand and contract, geomagnetic activity, daily variations, seasonal variations, and other factors. V is the velocity of the orbital object, which seems straightforward. but it's actually the velocity of the orbital object in relation to the atmosphere, and there are atmospheric winds in low Earth orbit. You therefore need a model that can compute that velocity for you. A is the reference area of the orbital object, and C sub d is the drag coefficient. Together, these provide another factor in the total amount of drag. Let's look at Starlink v2. Let's say that the Starlink is traveling directly towards us in this configuration, presenting the maximum surface area and therefore having the highest drag. If it is edge-on to the path of travel, it presents a much smaller surface area and therefore much less drag. And if it is end-on to the path of travel, it presents the least surface area and therefore the minimum amount of drag. The overall orientation is chosen by the orientation of the spacecraft that it needs to do its job and the orientation of the solar panels to catch the sun. These constraints may change over the course of a day or even during a single orbit as the trade-offs change. If you're over an area with few subscribers, perhaps you need less power and can put the solar panels in a lower drag configuration. All of these factors make it very hard to figure out how atmospheric drag might affect a specific spacecraft. The Earth is pretty close to a perfect sphere, being 99.7% circular. It's actually an oblate spheroid, with a slight bulge at the equator, and it's a little flat at the poles. The Earth is also not of uniform density, and that means that the gravity over one part of the Earth may be higher than over other parts of the Earth. These are small effects, but more sophisticated predictive models do take them into account. And the Sun and the Moon also have gravitational influence on the object, changing its orbit. These factors, plus a few others I've skipped over, mean that it's hard to get good predictions of the positions of objects, and therefore it's hard to identify possible conjunctions that are a week away. This is why it's so important to have continuous updates of tracked objects, so that you know your predictions are for as short of a period as possible. With the predicted path of all the objects we're tracking, we can get to the important part. The first step is conjunction assessment or conjunction screening. It basically calculates the paths of all objects and then looks to see if there are cases where there might be a conjunction. The second step is a risk analysis that looks at how likely a collision is. In this diagram, the objects are located at the black dots, and the ellipses represent the amount of uncertainty in the location of the satellite that exists based on the factors I discussed. The evaluation is something like, does the range of possible locations for the primary object intersect with the range of possible locations for the secondary object? The analysis spits out a probability of there being a collision. For NASA, if the risk is higher than 1 in 1,000 for robotic spacecraft, they will move the spacecraft. And as I said earlier, if it's a crewed vehicle, they move it if the risk threshold is greater than 1 in 10,000. If the threshold is exceeded, a maneuver is planned to move one of the objects enough to reduce the chance of collision below the threshold. There's not surprisingly a lot of math going on here, and a lot of research to make the process more efficient. This becomes more important as orbital objects proliferate. And that's all for part 4. Next time we'll be talking about what might be done to clean up this mess. Today's song is Space Junk, off of Devo's 1978 album, Are We Not Men? We Are Devo.